Hello everybody, welcome back to my basement. So I am here today to re-record the lecture that I delivered in Generalized Linear Models on February 3rd. Although I did remember to hit record, what had happened was that the video encoder got overwhelmed. I believe I had somehow altered the settings in a way that was ultimately detrimental, so the recording that I thought I had was actually only for the first 3 minutes of class. So I get to redo it. The class was held on Zoom only, so it wasn't super interactive to begin with, so you're not really missing too much from that perspective for those of you who are only following along with these videos. Welcome to you too. I am going to go through what we covered in a slightly different order than I did in class. Normally in class, I go through these handouts by order of concept. So like, here's the thing we're trying to do, here's what it looks like in SAS, then stated, then R. I do that so that we can focus on the concepts rather than the implementation, and so that there aren't long periods of time where people aren't going to be listening if they're not interested in that particular program. However, given that this is a video that can be paused, rewound, and fast forwarded, I'm going to go through the models that we covered by program instead. That way, if you're not interested in those pieces, you can easily skip. So just to recall, what we're doing here is going through example 1. These are fake data simulated on the basis of real data. So I have 550 older adults. We're looking at predicting cognition as the outcome from quantitative predictors for age, which has been centered at near the middle of 85 years for this sample. Grip strength, which is pounds per square inch, a measure of physical function centered at 9 pounds. A binary indicator for gender with men as the reference group, and then a categorical predictor for dementia status, which we're going to represent with 2 contrasts for none versus future and none versus current. So previously, on Tuesday or thereabouts, we covered the setup for the data with respect to creating the predictor variables, so centering the quantitative predictors, doing an indicator dummy coding scheme to set up the contrast to differentiate the 3 dementia groups. So I will refer you back to those videos if you need a reminder on how to do those things. And we had gone through the interpretation previously on this main effects model right here, and where we had started in class was on the extra pieces of code to get supplemental information in our output that is not readily provided by either the model fixed effects or the program and f-tests thereof. So this is our model. This is, let's see, what page am I on? I am on page 3. And this is what I would call a main effects only model, meaning that there are not yet any interaction terms. So I have a linear effect of age, a linear effect of grip strength, a linear effect of sex, which is the only kind possible given that it's binary, and likewise 2 linear slopes for group differences of none versus future and none versus current. So one of the things that we want to get right off the bat here is the missing group contrast. So anytime that you have a dummy coding scheme, the model is automatically going to give you the differences of each group relative to the reference group. What the model will not give you directly in its fixed effects are the differences among the non-reference groups, but they are available as linear combinations of those fixed effects if you know how to ask. So the logic behind that statement that we'll see in just a second is, how does the model tell us what the difference between the future dementia group and the current dementia group should be? It's right here. So this piece right here is the adjusted mean for the current group minus the adjusted mean for the future group. And so to get the difference between the future and current groups, it's beta 5 minus beta 4. The other thing that this model is not going to give us automatically, because of the way that we've created these categorical dummy-coded predictors ourselves, is an omnibus test of whether there are any differences across the 3 groups. So if we had let the program do the coding, then more than likely it would have provided us with what is known as an omnibus main effect of group in ANOVA language. So it would be a 2-degree freedom f-test about whether or not there are any group differences in the means across the 3 groups. We have to ask for that separately. So the other thing that I want to demonstrate, in addition to the missing pairwise group contrast, is how to lump these 2 slopes together in order to test the main effect of group as one idea. So group requires two fixed slopes to be able to fully differentiate the three group means. We want to put those slopes back together to make a joint test. So let's do that, starting with SAS then. So the process in SAS for lumping together any set of fixed slopes that you need to answer a particular research question is done via contrast. And I have two examples here, one for pedagogical purposes and then one that does what we need to with respect to dementia group. So in all of these purple words here inside the quotes, these are labels that you write. You can write whatever you want. You do have to write something though, because these labels are going to differentiate these contrasts within an output. So leave yourself a nice note as to what the heck you're trying to ask for. And as I said here, this contrast statement is going to replicate the model R-square F-test for whether or not the 5 slopes in our model work together to significantly predict variance in cognition. In other words, the model R-square is an effect size for how well these 5 slopes work together. I'm going to ask it to give me the corresponding F-test. So this is provided by default in general linear models. It is not provided by default in other kinds of models, such as the generalized models that we're going to be getting to very soon. So within these contrast statements, you would list each slope that you want to test against 0, followed by a 1. So it's effectively a multiplier. And the commas are used to differentiate numerator degrees of freedom. So this code right here understands that I want a joint test of all 5 slopes and that there will be 5 degrees of freedom. So basically the commas work to keep track of how many different things we're lumping together. So likewise, if I just want to lump together the 2 fixed slopes that have to do with dementia group, then I can just list those. So that's what I've done here. So contrast provides F-tests for multiple slopes at the same time. Estimate is another thing here. This provides linear combinations of fixed effects, so single degree of freedom tests, such as differences between slopes. So in this case, this is how I'm going to get the missing contrast between the future and current groups. I know from the math up here that it should be beta 5 minus beta 4. And in the wording of future versus current, current goes first here because future is the reference. So in the corresponding code, future, the difference between none and future, is listed first with a -1 because I need minus beta 4 in order for this direction to be consistent with how current differs from future. And likewise, beta 5 is given a 1. So the values that show up in these statements are the multipliers of the fixed effect coefficients themselves. So when you write dem nf here, you are not talking about the variable. You are not assigning values to the variable in this instance. What you are doing instead is referring to which fixed slope you want to multiply by -1. So the variable names are placeholders for what their beta fixed slopes are going to become in the model results. So I am telling it to take beta 5 and then subtract beta 4. So there's an implicit addition sign in between these two here. That is not shown, but that's what it's doing. Okay. Next, how to get predicted outcomes. The easy way and then the hard way. This is the hard way. So in SAS, you can write these estimate statements to create linear combinations of fixed effects that create an expected outcome. So in other words, a y-hat in a regression context where y-hat is the predicted outcome given the model predictors, not including the residual. So this is using the original equation and referring to what values for the predictor variables should multiply each of these resulting fixed effects. So the term intercept 1 right here means take beta 0, whatever it's going to be, that's what intercept means, and multiply it by 1. And then the next one, take age 85 and multiply it by -5 because the outcome that I'm trying to predict is for age equals 80. So because age has been centered such that 85 is now 0, the value of the centered predictor has to be -5 in order to create a prediction for an 80-year-old. Likewise, grip strength is centered at 9, so to get a prediction for somebody with a grip of 6 instead, I plug in a -3. And I have decided to hold all of these other predictors constant at 0, so this prediction is going to be for a man who never has dementia. So typically when you want to make a picture to demonstrate model results, you would pick low, medium, and high values of your predictors to show in combination, and those are all context dependent. In this case, I picked things that were somewhere near a standard deviation, so plus or minus 1 standard deviation, and then something near the middle. And I have a separate programming statement for each of the 9 predicted outcomes that I am going to create. Now, this is something I could have done in Excel to get the predicted outcomes, but the benefit of doing it within the software is that not only do you get the predicted outcomes, you also get their standard errors. So that is going to be very helpful in more complex models for making sure that you have the correct standard errors with which to create error bars or things like that on your plot. And I am saving this table of output into a SAS data set. So I didn't get a chance to talk about this in class, but so here's a little bonus for you. ODS output stands for Output Delivery System. It works to save the tables of output that you see in your results window as SAS datasets. So it functions similarly in R, how you can save model results as objects in the R environment, and then you can go into them and do stuff. It's the same principle. So each routine in SAS, such as ProcGLM here, has documentation for what internally, how it has named different output tables. So you can go into the documentation and figure that out. In this case, the name for the output table that is created by this code is called estimates. So I have saved the results of this table in a new data set called est_main_effects within my work temporary directory. So here are the results then in SAS. First up, beyond just the model F-test, which we discussed in class last time, are the contrast statements. So these are the additional F-tests that we requested lumping predictors together. And lo and behold, the F-test for whether or not the model R² is different than 0 is equivalent to the F-test here for whether the 5 slopes work together and to make a significant prediction. And so those values are the same because I just demonstrated for pedagogical purposes where that F could come from if it weren't already provided for you. The second one is the new piece of information that we don't have yet and wouldn't have unless we knew how to ask for it, which is the omnibus main effect for whether or not there are any mean differences across the 3 groups. Survey says yes, there are. And the degrees of freedom for the numerator are given right here. In these models, there's only 1 degree of freedom for the denominator, and so that's given up here. So 544 is the denominator degree of freedom for both of these F-tests. So then last time in class, when we actually did record successfully, we went through the parameter estimates here. So the one thing that's going to be new is the difference between these two. So if -5 is the difference of how future differs from none, and -16 is the difference of how current differs from none, I can take the difference of these two and get future versus current. So it looks like it's somewhere around -10-ish, -11, doing the math in my head. And lo and behold, that value is the first estimate provided in our output. So the missing pairwise group difference that is implied by the model as beta 5 minus beta 4 is given right here, along with its standard error, t-value, and confidence limits, and so forth. So if I wanted to use, let me see here, the rest of these estimates, so these are y-hat predicted outcomes for people who are low, medium, and high on age and grip, and create a plot out of them, here is some SAS code that does that. So what this next little piece is doing is going into this saved data set, and this label is saved as a variable called parameter. The index function goes inside and says, if these words are here, basically if you find it at some place in the function, then do something. So if the line of output, so this is saved as a row in this SAS data set, If it has this text in it, then set this new variable equal to 80. So I'm basically taking these labels and pulling the text apart so that I can create new variables to use as my x-axis for plotting age and grip. It's coffee this morning rather than Diet Mountain Dew since we're recording this semi-bright and early. So once we have that, then I can throw proc sgplot to work here. So I'm going to make a line plot in which I have grip strength as my x-axis, and the predicted outcome is saved in this column, which is called estimate in the SAS dataset. And I can tell it to group by age, so I get separate lines for different ages, and then I can set the axes and so forth. So this process of writing out a separate programming statement for every single plot that you want, every single point rather that you want to plot, this is a lot of work. So let me show you a faster way to do this. It's a hack. A pro tip, if you will. I am going to introduce you to the method of what I call fake people. And this is honestly what I do when I need to make a lot of pictures quickly with the same type of information. If you want to show all possible combinations of low, medium, and high across your variables, odds are good you won't have subjects in your data set that have the exact combinations that you want to show as prototypical values, but you can put them there. So I am going to literally make up a new data set of fake subjects. I have named my new data set Fake People, and it's going in the work library, which is the temporary directory where I do all of my things. That way the original data stays safe and sound. Input is how you list the variables to be entered. So these are the same variables that I'm using in my original analysis. In a weird order of operations rule, the data to be entered have to go after any transformations you want to do them. So first, I have just copied the code that I wrote before to create centered predictors for age and grip and to do the dummy coding for dementia. So that goes first. And then under data lines, I have provided values for each of the 5 variables. So I'm using the original variables because that's easier to think about, and then I'm letting the code do the centering and recoding for me. So I have entered ages 80, 85, 90, 6, 9, and 12 for grip strength. I'm holding gender at 0 for men, and I'm holding dementia group at 1 for none. So it's the same exact set of values that created this table. Note that I am not including a cognition outcome for these fake people. So as long as you do not give them an outcome, this method will work. So I'm going to take this fake data set. I know that they are fake people because I did give them an ID variable of -99, so that's my clue to myself. I'm going to concatenate my real data and this fake data. So within my example 1 data set, I am going to add these additional rows of fake people. Then I'm going to rerun the same model, adding this additional line right here. So this is not creating a SAS dataset out of output. It is creating a new SAS dataset with predicted values. So the out statement here is the dataset to be created. It's being saved in the work library, and it's called pred main, so predicted values from the main effects model is what that means to me. It is going to include all of the data that were used for the analysis. So it's basically creating a copy of the example 1 data set. But most importantly, it is adding a column for the predicted outcome, and I have named that column y hat, and it's adding a column for the standard errors for those predicted outcomes, which I have named SEY hat. So now I can go into that new created data set where for every single subject, real or fake, I now have a predicted outcome. I can throw that into the same sgplot that I had before, subset it to only the fake people. So where is like a filter, like use only if this is true. And then I can plot by age, or plot by grip at the separate lines for different ages in the same way that I had. And so this is the picture that I end up with either way. It ends up creating the exact same picture. So making fake people and then rerunning the model with them in it is a lot less work than writing out separate programming statements for every single point that you want to plot. This also is much faster and less error prone in models that are very complex with lots of interaction terms and things like that. So that is what I would recommend doing if you are going to use SAS. If you are going to use Stata, then you have a very easy way to get predicted values without doing any of that. So let me walk you through the Stata code. So if you're just joining us, we are focusing on what I call here a main effects model, meaning that we don't have any interaction terms yet, and two pieces of information that we don't yet have with respect to dementia group. So one is going to be the model implied difference between the non-reference groups that is available. It is implied by the model, but it is not available in the output unless you know how to ask for it. So we have the conditional mean predicted by the model for the current group minus the conditional mean predicted by the model for the future group. And so beta 5 minus beta 4 is going to tell us the difference between the future group and the current group. More specifically, how current differs from future as the reference. So future is the term that gets subtracted to make the direction work. Nope, not yet. The other thing that we need to do is lump these two slopes together to get an overall omnibus test of whether or not there are any group differences across these three groups. If you had told the program that group was categorical, it would probably provide this for you. I don't believe Stata does, actually. I think it's the exception to the rule, but most other programs would have. So given that Stata doesn't understand that these two things are connected, we have to ask it to lump beta 4 and beta 5 together to create my omnibus main effective group. So I'm going to do that with test statements. So there are two statements here. One is for pedagogical purposes only, and the other is to give us the effects of dementia group that we need. So this is the analog to contrast. And how this works is that within parentheses here, parentheses are used to differentiate differentiate each slope to be lumped together. So how many numerator degrees of freedom you have for this f-test is denoted by how many sets of parentheses you have. And within each parenthesis, you have to list what you're asking it to test. So this one is like, well, what if the age slope was 0? What if the grip slope was 0? What if the sex slope was 0? And so this is going to recreate what we know of as the model f-test for our R-square. So the joint test of all 5 slopes is the significance test that accompanies the effect size of how much variance was explained by this model, by these 5 slopes. The second one is the one that we actually need, and that is to lump together beta 4 and beta 5 to provide an omnibus f-test for whether or not there's any mean differences across the 3 dimension groups. LinCom, on the other hand, is the analog to estimate in SAS, and it provides single degree of freedom tests that are made of linear combinations of the fixed effects. So in this case, what is actually happening in the code is much more explicit because of the way that Stata requires you to write it. So dem nf here is being multiplied by -1, so that's referring to the minus beta 4 part, plus dem nc being multiplied by the 1, and that's referring to the beta 5 part. Obviously, I don't have to write the times 1, but I do that to keep the code looking the same across the 3 programs. So this is going to give us the test of beta 5 minus beta 4, which will tell us how the current group differs from the future group, how the non-reference groups differ from each other. Last but not least, Stata lovers, this one's for you. This one command is almost enough to make me switch to Stata. Stata anticipates that you might want predictions over a range of predictor values. So you can use margins to do a lot of different things, but one of the things that it does best is create predicted y-hat outcomes over a range of predictor variables values that you specify. So at allows you to provide quantitative predictors in a range, and how to interpret this little piece right here is indicated in the comment. It's from, by, and then to. So what this is saying is start from age equals -5, so that's an 80-year-old, in increments of 5 as the middle parenthesis and go up to 5. So this is going to give me predicted outcomes for 80, 85, and 90. Likewise, start at -3 in increments of 3 up to 3 is going to give me grip strength of 6, 9, and 12. And hold these other ones equal to 0 means make it for a man without dementia. So this is going to give me in one line 9 different predicted values, and it would have given me as many as I wanted to ask for. So if I changed, for instance, this increment to 1, then it would have gone -5, -4, -3, -2, and so on up to 5. Put that back. I had a question in class what V-squish does. It just removes the blank space between the results, so it takes up less output that way. So if margins wasn't cool enough, you can make a plot with the margin information that you just saved in one more line of code. So margins plot takes whatever you just told it to make and makes a picture with it. And you can tell it which predictor you want to be your x-axis. So in this case, I did it by grip. It then understands to make separate lines for the other predictors. You can create a name for it within Stata, and then because it pops up in a different window than the standard Stata output window, if you want to save it, you have to do so additionally. So I have code here to export it as a PNG file. And that file is inside your downloads folder under Stata plots. These are all the pictures that I made for this example. And you can see it below. So in the Stata output for this main effects only model, this term here, that's your residual variance. It's called mean square error. In other programs, it's mean square residual here. Here's my f-test for the model and the r-square that goes with it. Here are the coefficients. So these are the fixed effects directly estimated by the model. This is the intercept. So much to my great dismay, Stata puts the intercept last, no matter what. I haven't figured out a way to change it. If anyone out there is listening who knows how to change it, please let me know, because I would really like to do so. Then we get the extra stuff that we asked for. So the test statements to do joint f-test of multiple slopes at the same time. Here's the one for the f-test for the model. So this perfectly recreates what we had up here as a demonstration. And then the one that we actually need, this is the joint test of whether or not there's any differences across the 3 groups. So that's our 2 degree of freedom test for additional information. And then here's the Lincom statement that we asked for to get the missing group difference among the non-reference groups. So -10 is how current differs from future, and that is given to us as the difference between those 2 slopes. So the current group's slope is more negative by 10 and some change here. That's how I would interpret that. And then last but not least, here is a subset of the margins results. It does not do you any favors in how it labels them. This output table is preceded by a very long table with better labels, but here's the picture that it creates. So it does so in a fairly efficient manner. Next up, R. So here's our model again. If you fast forwarded to this section, then I'll say the same things again for you. I am calling this a main effects model because there's 5 predictors that have slopes here, and there are no interactions. So we have linear effects of age and grip strength as quantitative predictors. We have a binary predictor for gender with men as the reference. And then we have 2 binary predictors that capture differences of each of the dementia groups relative to none. So beta 4 tells me how the future group differs from the none group. Beta 5 tells me how the current group differs from the none group. And with respect to dementia group differences, I want to request 2 additional things. One of those things is the difference between the non-reference groups. So the difference between future and current is not directly given as a slope in the model, but it is implied by the slopes in the model. More specifically, if I figure out from the model what the adjusted mean or the conditional mean should be for the current group, and subtract from it what the conditional mean should be for the future group, that leaves me with beta 5 minus beta 4 as how the current group differs from the future group. So I can ask for that as an additional hypothesis test available from the model. Likewise, because we have denoted our dementia groups using these indicator dummy variables, R doesn't understand that those two things are actually working together to describe pieces of the same variable conceptually, which is this three-group dementia variable. So we want to ask it to provide us with a joint test of beta 4 and beta 5 so that we can decide whether or not we have an omnibus main effective group, as it is known in ANOVA language, whether or not there are any mean differences across the three groups. So this is a 2-degree of freedom test that would lump together beta 4 and beta 5. So let's see how to get those additional pieces of information. So I am using linear models here in R. I'm saving my model results as model main, using example 1 as the data. Here's my formula. Cognition is my outcome. Squiggle means equal, since equal is already taken. And I have included a 1 here, even though I don't have to remind myself that the intercept is the first fixed effect. That will be relevant here in just a minute. So then I have the rest of the fixed slopes that I have requested for these predictors. I am asking for the output to actually be printed, and because the generic output that's provided by default does not include residual variance, and I couldn't figure out how to get it to do so, I'm adding an additional ANOVA command that will spit out the residual variance for the model. And by the way, within the example files, so this download folder that has all of the data syntax and output across the 3 programs, if you'd rather follow along in R to look exactly what the output looks like, it's in here. Of course, it's not going to open right now because I'm recording. 1 second. Okay, I'm back. The output is formatted a little bit down below, but it's not terribly pretty. So we'll get to that in just a second. But the original output is available inside this download folder. That's where I was going with that. Okay, so now the extra pieces of information. First, to be able to lump together these 2 slopes to get an omnibus group test, I want to show you how that would work. So I have 2 examples of these types of lumping slope tests. One of them is going to recreate the model F-test for pedagogical purposes, and the other is going to give us the 3 dementia groups difference test. So GLHT is what we're going to use in R. It stands for General Linear Hypothesis Test. And there's a couple different ways that you can specify what the hypothesis is that you want it to test. So I'm going to demonstrate a couple different ways in this example. One is this way. So what is the linear function that you want? And we have to concatenate several things together. So this looks somewhat like the Stata code in that we are making explicit that I'm setting this slope to 0, this slope to 0, this slope to 0, and so forth, where the commas are going to indicate numerator degrees of freedom. So it understands that I'm asking for 5 separate slopes, all to be tested at the same time. The all to be tested at the same time part is a result of this option within summary. So if you don't have that there, it will just spit out the results of each separate slope being tested against 0, which is what we'll already have from the model. So that test equals F-test asks for a joint test. Likewise, if I want to get a joint test of just these 2 slopes so that I can have an indication of my omnibus main effective group, then that's a second command, same setup, but now I'm asking for just these 2 slopes to be lumped together. So that's going to be my omnibus group main effect, as it says here. And then last but not least, you can also use GLHT to get single degree of freedom linear combinations of fixed effects. And this is why, let's see if I can fit it on the same line here. This is why I have the 1 in my code. So this right here, you have to know in order to understand what this right here is doing. So the values to be entered in this string of numbers here, each value order corresponds to the order of the fixed effects as they are returned by R. In this case, it will be returned in the order in which I've written them, starting with the fixed intercept and then continuing with the rest of the predictors. The actual values themselves are the multipliers that you would use for the fixed effects as they are estimated by the model. So in this case, I don't want anything to happen with respect to the intercept, so shut that off at 0, with respect to age and grip, or with respect to sex, because I only want an operation using the last two slopes. So this minus 1 times beta 4, and then 1 times beta 5 is going to give me this beta 5 minus beta 4 linear combination that will test how the current group differs from the future group. So that's my missing pairwise group contrast. And by default, this procedure wants to mess with your p-values in various ways. To make sure that my output looks like that of all the other programs, I have turned that off. So these are just straight up p-values. You can worry about type 1 error on your own terms. Then the longer way of getting predicted outcomes, so this is analogous to what I had to do in SAS using separate estimate statements. The hard way to get a predicted outcome is to write a separate line of code for it. So I have created predicted outcomes for 9 different hypothetical people here. That would be low, medium, and high on age and grip strength. So for instance, an 80-year-old, to create a predicted outcome for an 80-year-old, I need a 1 in the first place because that refers to me needing beta 0. So all predicted outcomes at a minimum start off with beta 0 for the fixed intercept. The question is then, what other values of the predictors do you need to include in the linear model? So because I want a predicted outcome for an 80-year-old, I put in a minus 5 where age goes. I put in a minus 3 where grip goes because I want it for grip strength equals 6. So these are centered values. And then I am holding constant gender and dementia group at men with no dementia. So I've got all combinations here of low, medium, and high, creating 9 different hypothetical values. The reason that one would do this is because if you want to show what the model predicts as a function of your predictors, combinations of low, medium, and high is a pretty intuitive way to do that. However, you may not have actual people in your data set that have the exact combinations of the predictors that you want to show in your plot. So you can ask for these additional predictions per hypothetical individual just so that you can get a picture made out of it. So this is the long way to do this. I'll show you in just a minute a shortcut. So here's the results in R. So it gives us the fixed effect coefficients. And I have tweaked the code online so that it does not use scientific notation. So if you run my program, you can choose whether or not you want like 16 zeros here or the scientific notation. So those are the same tests that we got out of the other programs. We have then the, let's see here. The R-square for the model shows up here. And here's the f-test for the model. We're going to see that down below. And then the ANOVA command duplicates the significance test, but it puts it in an f metric. So for instance, t squared right here is going to be f. Like, does that look right? Yeah, I think so. Yeah, that doesn't look right. I don't know what the hell that is actually telling me because the p-value in the f doesn't look right. But point being, it might be a different kind of sums of squares. But this is what I wanted out of it. So this is what we would call mean square error or residual variance. That's the reason that I did this. It's for this number right here. Then the extra pieces of information that we got out of GLHT. So first is a duplication of the model f-test. So it was provided for us right here. If I had to ask for it, this is how I would have done so. So the GLHT command that shuts off all the slopes at 0 simultaneously gives me this global test. Likewise, the new piece of information that we would request about the omnibus main effect of dementia, that's right here. So it's setting both of those slopes to 0 simultaneously. So this f of 67 says, yes, there are differences across the 3 groups. And then last but not least, here is the difference between the non-reference groups. So if I go up to the model coefficients, it looks like future differs from none by -5, current differs from none by -16. So the difference of these two, it looks like current is more negative, so it's going to be smaller by about 11-ish, 10 to 11. And so that exact estimate is right here. So that is the difference of how current differs from future. Now, to make predicted outcomes, to do this more simply, we're going to use a predict function. So this is the method that involves first creating fake cases and then using the model results to create predicted outcomes for those fake cases. So I did this in SAS. There is no harm in doing this because the fake cases that we're going to be working with do not have real outcomes. So there's no way that they could screw up the model. We're just using this additional set of fake people so that we can create predictor values of the levels we specify, so particular low, medium, and high values in all combinations, and we can use the model results to get predicted outcomes for these new fake people. So I am creating a column of the values for age that I want to include, and then a separate column for the values of grip that I want to go with them. So I have 3 by 3 creating a 9-person set of data. I am then going to put those two columns in a data set. So the name of my data set is FP, which stands for fake people. I have added in a person ID variable of -99. That's to remind myself that these are fake people, if I were to look at it. And then I am going to send over my fake variable for age into the real one, my fake variable for grip into the real one, and then I'm holding the other predictors in the model constant. I'm holding it constant at men is 0 and dementia group 1 for no dementia. Then after that, I just borrowed the same code that I did above to center my quantitative predictors and to do my dummy coding for my dementia groups, just swapping out the name of the data set so that it's doing this in the fake people instead, because it's much easier to think about the original values when you're inputting this part and then just have the code do all the centering and coding for those original values. And then last step, I am adding to my fake people data set a new column where the new column is going to be called y hat main, so y hat from the main effects model. And then I'm using a function predict. So predict is going to go up into the model results that I had saved as model main, so that was where the linear model call was, and it is going to use my fake people to create predicted outcomes and save them as this data set. So I'm basically just adding a column to the fake people data that will contain predicted outcomes for those fake individuals, and then I have a picture. So I told everyone in class I was very proud of myself because this is the very first picture I've ever been able to make R make. I know it's not fancy, and I know it's not ggplot or tidyverse or whatever the hell. It's just base R, but it's a picture, and I was very proud of it. So to save the picture, I'm opening an output file. Then I have the plot, and then this closes the file. So this is how you can save the pictures that show up in the RStudio window to external files. I think most of this is fairly self-explanatory, so I'm telling it how to make the lines and what the values are in terms of where in the fake people rows I'm extracting this information from, and then adding legends and stuff. So in your homework for this class, I'm never going to ask you to make a picture, but I do want you to have examples of how to make pictures because they are very important in doing data analysis and conveying its results in real life. So this method here of creating fake cases and then using the model results to predict outcomes to be plotted, that's going to be much more efficient, less error prone, and especially so when you start getting into very complex linear models with lots of interaction terms and that kind of thing. So you can also potentially save a column for the standard error of the predictions. I didn't do that here, but I'm sure there's a way to do so. So there's my picture. Okay. Changing gears then. I think I'm gonna stop.